Good afternoon, ladies and gentlemen. As I have two honors, good to see everybody here today. We're going to pick up where we left off yesterday, which was in this vocabulary. And somebody noticed in sixth period that we have 4 blanks, yet how many answers are available here? 6. So we're going to figure this out. So blank is the set of first elements in an ordered pair or table. What is that going to be?
Function.
Okay, here's an ordered pair table, right? If we have an ordered pair like this first is going to be, if we have a set of ordered pairs, right? 2, 3. This set of first elements is going to be called what?
I'll count this, I believe it now.
Domain.
I know what it is.
Domain.
I believe it.
Domain, yes. Okay, we have Ashton here who's exercising faith, and that faith has been you haven't disappointed Ashton, so that's good. Blank, a value for the variable ordered pair that makes an equation true. Somebody said it. Some girl voice said solution.
I didn't even write it down.
Solution, a value, okay? Blank is a type of problem that often has a set of answers and can be written in interval notation. In fact, there might be an example of one of those types of problems earlier on your sheet someplace.
Inequality.
Inequality, very good. Whoops, if I could spell inequality, that'd be nice. Blank, a relation in which every input has exactly one output. Function, very good, I like that. And by the way, toward the end of class today, there's a song about that.
Yes.
There is. I don't have songs for every day, for everything. I have a few of them that, so.
You
See
didn't
how-
finish the song yesterday.
Oh, I didn't quite finish the song yesterday?
You should play it.
Maybe. I'll play late, toward the end of class. We'll do toward the end.
You wrote it on the board so we could sing along. Why didn't you do that for them?
Oh, yeah, we're going to do, I wrote part of it. I'll do that eventually. That's a good idea. Thank you for that suggestion. We may not do that today, but we will eventually do that. That's a good suggestion. All right. Now we have this next section. That's good. That's one reason she's here, to help me remember the things that otherwise I might forget.
Maybe she can sing it for you.
No.
She has to read
along with it.
We can just do like a little sing-along.
Yeah.
That's what it is. That's what's supposed to be.
And nobody wants to sing Charlie.
We just need a word sheet.
You're gonna have it. The main part is the chorus of the song, right? You gotta have a chorus. You gotta remember,
I
right?
want to see the chorus sheet.
Yeah, the chorus sheet. We'll do that. But now she's right. I did put that up there on the board 2 years ago. She remembers from 2 years ago. That's really good. Okay. Change to slope-intercept form. Here we have this. Find the slope. Use those input values for x values. Make a table. Plot the points and graph. Find the y-intercept by setting x equals 0. Find the x-intercept by setting y equals 0. So, well, how would you start this out, this particular set? It's really kind of a set of multiple things they're looking for. How would you start it out? Pardon me?
I believe in them. I believe
Believe
in
in them.
this.
Plug it in. Plug in each.
Yeah, okay. So,
It's a X.
yeah. So what Sierra is saying is that you can plug in each one for x, and if you do that one at a time, you're going to find what the outputs are, right? What I'm going to do here is, somebody in sixth period suggested a first step might be doing this. Just kind of writing these values in the table. And then what Sierra said is right, in that you could, if you just go ahead and set each of these values, if you set the x value, you'd solve for that. But there's probably a more efficient way of doing that, right? What's the more efficient way of doing it than what? Now Sierra was not wrong, but what's going to be maybe what's going to lend a little more efficiency to the operation here?
Can we put it in your calculator?
You can put it in the calculator, that's right. I'm going to assume that at this point it's a non-calculator problem, but yes. Well, how could you put this in the calculator though?
You gotta open it. You can't because the calculator doesn't have y-intercept form, so.
Yeah, see, the calculator, the default value for at least this kind of calculator is this, right here, in the slope-intercept form. And so what are you going to have to do to this? You have to change your equation, right? So let's go ahead and do that. So we got this 3x minus y equals 4. So how are we going to fix that? Subtract 3x, okay? Subtract 3x. And so we have left negative y equals 4 minus 3x. And then what? Divide by negative 1. Okay, very good. So if we divide, I'm going to put diagonal slash there, divide by negative 1. So we get y equals 3x minus 4. So now we have this, and by the way, it says change the slope-intercept form. There it is, right? So that is our slope-intercept form, isn't it? Okay, so what next? So now we can do what Sierra was talking about, right? Pretty easily. But it's going to be even easier. What's our y-intercept?
That little negative 4.
Negative 4, right? So a negative 4 we can put here and here. What's our m going to be? 3. So how can we fill in the rest of these pretty easily?
You got the thing. You multiply that x number by
Negative 1 would be negative 8.
Yeah, and so what Ashton's saying, you could do that, but if you have a table, it's maybe even a little easier than that. Because we can just add 3, right? So add 3, we get negative 1. Add another 3, we get negative 1 plus 3, 2. And going down here, we could subtract 3 and get negative 7 and negative 10. And so now we can plot these, right? So negative 2, negative 10, negative 1, negative 7 is right. Actually, I think it's supposed to be right. It's right there. So we got this here and 0, 4, 1, negative 1, 2, 2. So something like this, right? Okay, what's going to be our x-intercept?
Zero.
Nothing.
It's going to be
1.5.
1.5? Okay, that's 1.5 is not exactly, if it's very close, that's what Noah said in 6th period, but he was very close. Graphically, it kind of looks like a 1.5, doesn't it? Okay, so that's good. So that's going to be close. Let's go ahead and really find out what it really is. How do we find out what it really is? What we do is we substitute in 0 for y, right? So that's going to leave us with 3x is equal to 4. And so what is x going to be equal to? 4 over 3. So we got 4 over 3, which is like, what is that, 1.333? That's pretty close to 1.5, isn't it? And now, have we done everything here? Yeah. I think we've done everything on this, haven't we?
Yep.
I don't know what they have all these grids here for on this way the sheet is, but that's going to take care of it. Okay, distributed property exercises. How do we do this?
First things first, you're gonna wanna take that 8K and then multiply it just by the distributed property over that 2K and the 5, which will give you 12K3 and then 40K.
Minus, looks like
Oh, yeah, and
16.
also the 8K is negative, so.
Looks like 16K. Looks like minus 16K cubed, right? And then minus 40K. And then what do we do next? Combine.
Basically, we combine like.
No.
I have 6K minus 11 somehow, so I'm gonna use this.
No, I was gonna do something.
'Cause I added the-
wrong.
I did it
Does
wrong.
Does that look right? Did you find out, you know what, where you went wrong?
Yeah, because I didn't distribute first.
Okay, that's good. Glad you learned something from it.
I didn't.
Okay, next, this one here. So one way to do this that I've been telling the students to do for years and years, if they're interested, is work out something like this. Have any of you done something like this
In biology.
in biology?
Punnett square.
Yeah, it's like a Punnett square. Did you say biology?
Yep.
I think she did.
You said, yeah, it's like biology. It's just like the Punnett square thing, right?
Yeah.
And so, so a lot of these things we do in mathematics and science have some applicability and transferability between things. Sometimes when you least expect it.
Yep.
So now, what do we have when we multiply these things together? 7x squared, negative 14xy, and then negative 2xy. And finally, we have 4y squared.
We did some geometry last year.
And so, so we have 7x squared minus 16xy plus 4y squared. And this is a neat little exercise because it kind of combines the distributive property and combining like terms too, right? So that is that. What I want you to do is I want you to get out your notebook. We're going to take some notes today for a little while. And we're going to start on section.
Do you not like have a table of contents or anything for this class, or you just start?
No, I don't. Let me show you something. I want to show you something.
I never looked at it.
That's still a good question.
Oh my God.
Right here, okay. We're going to take some notes today. Who's asking about table of contents?
I was just wondering.
Now, what it is
Are you guys?
it's a lot of it, what we're doing roughly is here. So it's really kind of what's in the book for the most part. We're not going to go through strict chapter order. That would be what our table of contents is, and you break down the chapters, you have like so more detail. So that's what we're using those.
Okay, thank you.
Sure.
Are you trying to get for notes?
So Lily makes a good point, because even though you're not going to have a book in your hand most of the time, we are using material from the book, essentially. Okay. We're going to start out talking about domain, range, and end behavior. And the essential question, how can you determine the domain, range, and end behavior of a function? You don't need to write the essential question. I'll tell you what you need to write. So that's just kind of like an introductory, thought-provoking question, is what it is. I don't know if you have an answer to that question. But that's probably what we're going to learn about today. We're going to learn about,
The title is chapter 1.1.
yeah, chapter 1.1. Chapter 1.1, domain, range, and end behavior. That would be a good title.
Okay.
Yeah, so that'd be good.
Wait, we were supposed to write the last slide.
Okay, I just put down chapter 1.1, domain, range, and behavior. That's all we need to deal with here. And so we're going to go over some key vocabulary today, and mostly we're going to start talking about interval today, what an interval is. We may not get much farther or any farther than that. Okay, an interval.
I can't even see.
You can't see it? I don't know if I can, see, I'm not really, I can expand it a little bit.
I was like saying it. That's what I was saying in my head. I was like, oh, where?
Who's having trouble seeing it? Right here? Charlie, you having a little trouble? You having trouble seeing it? I don't know if the idea is copy from a neighbor or
It's just because.
talk to a neighbor about it maybe, because we really have trouble getting seats closer. So Charlie, a little bit nearsighted, is that it? Yeah.
What are your glasses?
I'm really nearsighted. I'm telling you that if I didn't have my contact lenses, I would have to go
Yeah, I know.
walk right up to it to see it. And that's another issue for this class. What I'm doing for my smaller classes is I'm keeping this column of seats vacant. Well, what's going to happen? I'm going to have to walk over here right in front and block Madeline's view from time to time. She doesn't look like she's getting really mad about it yet. And if I block your view, is that going to hurt you that much? Okay. Okay, what we're going to do is, the next thing I'm going to do is show you like a number line example of that. So here's a number line example of a finite interval. And this interval right here is written in what I like to call number line notation. So you can call it a linear graph, I like to call it number line notation because it's a way of describing things. And then below that I have, it says greater than -5 to 3. So greater than -5 to 3 is how you would verbalize what you see on that number line, right? Greater than -5 up to and including 3. That's what that is. Does everybody have the finite interval done
Here,
here?
need to draw that little graph.
You could if you want to. I'm not, and that's not going to be a hard one to draw. You can just draw it like this. Maverick, what I would do is I'd just write -5 to 3
Okay.
and just kind of make a simple version of it,
Okay.
like this, and then like this, and then like this. You can just draw it simply like that, right? Okay, next. An infinite interval is unbounded at one or both ends. Make it a little bit larger here. So one over finite interval and infinite interval. And this infinite interval is x is greater than -4. That's how you would say that. You need me to go back a little bit? Yeah. Try to make it a little bit larger too as I go. Okay, ready to go on the next one? Charlie, is this helping you at all to make it a little bit bigger like this? See it a little bit? Okay, next, we have a situation here. Suppose an interval consists of all real numbers greater than or equal to 1. You could use the inequality x is greater than or equal to -1 to represent the interval. So this one right here is what I call inequality notation. Inequality notation. And this one here of the notations that we're dealing with here, this might be the one you're most familiar with. Does it look familiar to you? Yeah, okay, good. Yeah, sure, good, yeah, sure. Oops. Pull that one up. Yeah, but the thing about it is that's going to be an issue for, you're going to be having like, you could do it today, but you're going to have like class meetings on Monday where the administration will really discourage that. So I don't know if we eventually want to rotate you to a forward seat or something like that, maybe. Because that's going to be that's just going to be an issue eventually. Okay.
Okay.
Okay. You need to leave it here for a little bit still?
Just a little bit.
A little bit, okay. So Carly, does any of this look familiar to you at all? No? That's what I noticed yesterday in this class. People were saying, wait a minute, I forgot everything. But do you remember ever having remembered anything like this before in your life up till now? Kind of, maybe? Okay, let's go on here. So, here we have a little statement that says, here are the types of notation we'll be using to describe intervals, domain, range, and function notation. And verbal and number line are ones we've already talked about. We talked about inequality notation, but we're also going to have notations we call set and interval notations. Remember we started working on Algebra 2 Builder yesterday? Remember that? Well, what we did is we had people ask, one of the things was they asked for set notation, right? On one. By the way, this I'm going to want to have somebody pick up the Algebra 2 Builder. And Ashton, can you do that for us? Yeah, Ashton can pick up your Algebra 2 Builder #1 assignments there. Thank you. So we're going to be going over set and interval notations quite extensively. And
Yeah, they did.
a notation is a type of language or convention of describing things. And these notations can be used, are used in what we're looking for to describe intervals. Now, how many of you are football players here? So some of you here are football players, right? Yeah. So Savannah, you powder puff football player, is that?
No, I was just kidding.
Oh, you're just kidding? But you know powder puff football is a real thing, right?
Yes.
Yes, okay. Anyway, what happens is, on the sideline, the offense has the ball, or even the defense, right? Is somebody's gonna hold a sign out for the offense or for the defense. What is that sign gonna say? What is that sign that on the sideline the coach or holds out? So, yeah, thank you, Ashley. What's going to be on that sign? The play, right? It's going to be the play, and it's going to be written in a certain type of notation or language. And why it's going to be written in a certain type of notation or language? It's going to be a language that the other team doesn't understand, that your team understands, right? So that's type of notation. So that's what we're going to do. Now, the last thing we're going to have in class today is this thing right here. I want you to copy this table. It's kind of a table, kind of a guide to notations. And so that's really the last thing I want to have in class today.
Go back to that one, just real fast.
The one, this one here? Yeah, okay.
Thanks.
I can go back.
I got it. I got it.
Got it, okay. Yeah, I have it, okay. So here we are. I'm going to go ahead and save it to save the larger file size. But and what I'm going to do a little bit later in class, toward the end of it, is I play a song while we do it. It has to do with what a function is. I don't know if you're going to like it. Sixth period said they liked it. So. So, again, did I ask you yesterday, do we have guitar players in this class? Oh, that's right, you did say that. That's right, Charlie did say that. And we're going to go over examples. Now, eventually that column on the right, interval notation, that's where we're eventually going to direct most of our energy to understanding of ways to describe intervals. So we will go to that. And if you look at the inequality column versus set notation, it's almost like that inequality notation is just set inside the set notation to what it is. You'll see that.